In this video, we're going to talk about radical halogenation, which is pretty much the only thing you can do with an alkane besides burn it. Okay, with combustion, you have a hydrocarbon that reacts with O2, and basically every bond in the molecule gets destroyed and replaced by oxygen in a way that's going to satisfy the octet rule. But that's kind of a destructive reaction. Like, you can't really do anything with the products, it's just CO2 and water. In order to make a building material from an alkane that we can use for organic chemistry reactions, well, we're going to do something called radical halogenation. So that all starts with an initiation step of something that's easy to form a free radical with, typically a halogen. So a free radical is an atom or molecule that it's breaking the octet rule. And essentially it results from, and if we're going to look at bromine, for example, here, the initiation step here is when UV light hits it, it has enough energy to break the bond. But it breaks it in a weird way. It breaks it evenly. We call it homolytic cleavage because it takes the bond and it splits it in half. So now you have a resulting 2 bromine atoms that have 7 valence electrons, which breaks the octet rule. So it's not stable, and that's why it's reactive, because it doesn't want to stay like that. So in this, we're going to use for a propagation step, we're going to use the molecule ethane. So ethane, just 2 carbons, fully saturated hydrocarbon. Bromine, the free radical atom, will collide with one of the hydrogens on it. And when it does that, it forms another homolytic cleavage on the carbon-hydrogen bond. So what we end up with is a free radical ethane and then HBr, hydrobromic acid. So now this isn't stable, and this can do a number of things from here. Could combine with other ones like this and make butane, but the most common reaction, just to go for simplicity's sake at this point, is we could have a termination step where bromine, free radical, then combines with that. And that's going to end the free radical chain reaction setup that could happen. Right? And you end up with a brominated hydrocarbon, which really gives us a place to do stuff now. We can have substitution reactions, we can have elimination reactions from this, and now we have a building block from which we can synthesize something. Now, ethane's about as simple as it gets, and the one other thing I want to focus on is like the stability of these free radicals. Now, the more substituted a carbon is, the larger the surrounding electron clouds are that can contribute to stabilization of this free radical. Because again, it's not stable. But the bigger the electron cloud is around it, the more happy it is. Okay? So the more substituted, the better off we are. So if we had this would be a tertiary free radical, that would be the most stable. Other than that, you would have secondary, and then primary, and at most simple level, you would have the methyl free radical. But essentially, the more substituted, the more stable. So that's your most probable place where you're going to have a bromination or a chlorination from a free radical reaction. So that's all for today, folks.